All right, great. So I think everybody's in our room now. And I want to welcome everybody to our second RCPCE ENGL Zoom talk. My name is Professor Kathleen Ahrens. I'm the director of the Research Center for Professional Communication in English. And I'm going to introduce Dr. Dennis Tay to you. And then we will, Dr. Tay will talk to us for about 40 minutes, and then we'll have about 20 minutes for questions. During the question period, I'll ask that you raise your hand or unmute your microphone, it's fine, and ask a question. Please say who you are and where you're from. And you may also ask questions in the chat, but just to be warned, it can be hard to see if a lot of questions come in at once in the chat. Your safest bet is to unmute your audio and ask a question, okay? And please identify yourself when you use the chat as well. Okay, so those are the preliminaries. I'd like to welcome Dr. Tay for giving this talk. He is an associate professor in the Department of English. His research covers 4 overlapping areas: cognitive linguistics, metaphor theory, mental health care communication, and discourse data analytics. He's the academic editor of +1 and the associate editor of Metaphor and the Social World, and also Metaphor and Symbol. I had the pleasure of listening to a short version of this talk last week when he gave it to the Hong Kong Academy of Humanities. He is an early career fellow in the Hong Kong Academy of Humanities, soon to be an associate fellow, and I'm looking forward to the full version of this talk. So without further ado, let's welcome him. Dennis?
All right, thank you very much. I hope everyone can see the slides. Kathleen, can you see the slides?
Yes, I can.
Okay, good. So I'll go ahead and start. So thanks a lot to ENGL and also RCPCE for organizing this sharing session. So my talk today is called Surveying the Discourse Roulette, addressing poverty of data with Monte Carlo Simulations. Okay, so the outline. First of all, I will just clarify what I mean by poverty of data. You know, usually we talk about poverty of stimulus, but today I just changed the phrase a little bit. It's a very common issue in professional communication slant discourse research, as most of us will be able to relate to. And then I will briefly introduce. Today, I must say it's a very introductory lecture because of the shortage of time. What is the Monte Carlo method, or Monte Carlo Simulations, MCS for short? I will zoom in on a case study of how we apply this method to the study of psychotherapy language, particularly in the scenario where we don't have enough empirical data, we simulate the data instead. I'll start with an overview and then illustrate the MCS methodology as it is implemented, and with a focused illustration on one specific variable, which is called analytic thinking. And then finally, some conclusions about how we can apply the MCS models more generally, and most importantly, some limitations and drawbacks of this approach. Right, so poverty of data in PC and discourse research. We know that authentic and high quality data can be quite hard to get for PC and discourse researchers. So some examples include call centers. I know some of us are working in this area. Classroom discourse between teachers and students, workplace emails, and of course, psychotherapy as well. These are all examples of PC and discourse research, and all examples where authentic and high quality data can be hard to get. What are some of the reasons? Well, obviously, the most important one is confidentiality. In these contexts, not everyone is willing to share the data. There's also the issue of the observer's paradox, where, you know, by the very fact of observing or even knowing that you are being observed changes the very nature of the discourse itself. And then, of course, there are logistical issues surrounding data collection. So the problems, what is the effect of all these difficulties? Obviously, to do with validity. Right, if we don't have enough data, we may not be able to actually analyze what we are supposed to analyze, and of course, representativeness, and also ultimately applicability. How useful are your results if we don't have enough data to begin with? Some solutions, well, obviously, the most straightforward one is just to do something else, change your topic, and of course, make more friends, get more data, and I find this personally to be very difficult. And of course, we can hatch our claims, so limited data, we just don't claim as much, and also in some contexts, we role play. For instance, in professional communication as well as psychotherapy, the role-playing methodology has been used quite a bit, whereby instead of real participants, we get to pretend that they are actually doing the thing that they're supposed to do. So today I want to talk about yet another completely underexplored solution, which is Monte Carlo simulations. In other words, simulating the data that you don't have. So for instance, in professional therapy databases, like the one on the right that I've been using for a long time, there's a subscription fee, so it's supposed to be high quality, it's supposed to be authentic, but we notice a lot of gaps in the data. So within a dyad is basically a therapist-patient pair. So within a dyad, we see a lot of missing data, so up to only about 60 to 80% of all the sessions in total. So psychotherapy occurs in weekly sessions. So for instance, the average number is about 20 sessions per person. But we see only 60% of these sessions are actually eventually recorded and transcribed. And then across dyads, we see a lot of gaps as well. So many people are understandably not willing to participate in such data collection measures. So however, this is not the end of the world, because if aspects of the data, and this is the interesting point, because linguistic data is not traditionally regarded as quantifiable, but if we can somehow measure different aspects of the discourse, then we can run numerical simulation techniques to fill in the gaps of the data that we cannot actually observe. So I will discuss the MCS, or the Monte Carlo method, today. Right, so you can see on the picture, this picture is actually the Monte Carlo casino. So some of us may know the Monte Carlo, of course, it's a famous casino gambling resort. So this method is kind of associated with it. It's not directly named after it, but because of its obvious applications in like gambling, as I will demonstrate later, it's come to be associated with the name of the method. So basically, the basic idea is to use numerical simulation. So what happens is you generate all kinds of numerical data to actually represent the phenomenon that you cannot observe directly. But this generation, of course, is not random. It's based on a probability distribution underlying the sample data that you actually have. So we do this to predict the outcomes of a particular random process. So this is most useful when, number one, the actual observations involve uncertainty or randomness. And this is certainly true for a lot of things in the world, including the use of language across different psychotherapy sessions. And also we use this when the actual observations are hard to come by. So this is actually the important motivating point for today's talk, whereby in a case where you don't have empirical data, you can use MCS to substitute for it. So this MCS is very common in fields like finance, engineering, AI, gaming, etc. And it has never been actually applied to language data. Even though some of these fields, for example, in gaming, it may involve language, but I haven't seen anyone use this method before. So this is very exploratory. Right, so to illustrate this method, let me just use the example of a casino roulette game. So you see from the previous slide, a roulette is basically this thing here, whereby this wheel spins and there's a ball inside, which eventually ends up in a particular slot, and then you bet on the slot. If the ball ends up in the slot, you win. If the ball doesn't, you lose. Right, so just to illustrate what I mean by MCS. So the very initial conclusion I can tell you already is that the house always wins in the end, and you will always lose if you bet a lot, right? So despite the fact that at the beginning, it seems like your odds are equal. So imagine a roulette game where the house has a 51% chance, just a very slight advantage over you. So you can imagine this as, for instance, there are 51 slots which are not favorable for you, and 49 slots that are favorable for you, right? So therefore, for each spin that you make, the house has a 51% chance. Imagine that. So this is a very basic probability distribution. We call it a binomial distribution. So you either win or lose, and you have 49% chance of winning. So just statistically speaking, without any data, you can expect to win 49 per 100 spins. However, bear in mind that there will be random variation. So for instance, by the binomial distribution, there's a very high probability that you can expect to win at least 40. In fact, it's 97% chance that you will win at least 40. All these can be calculated quite straightforwardly. And there is a 13% chance that you will actually win more than 55 spins. So it is quite a low chance, but not entirely impossible. 13% is not exactly very low if you think about it. And of course, the probability of winning more than 70 out of 100 spins is very, very low. So you don't expect to go to these territories. But the point here is that this point, random variation. So you expect to win this amount, but there is random variability, right? However, the important point here, the key point about MCS is that if you repeat these 100 spins multiple times, so many people come to gamble, so multiple sets of spins, all these different scenarios of random variability will eventually unfold by the laws of chance itself, right? So therefore, in the short term, it seems like you have an equal chance versus the house. I mean, this is quite good odds. It seems to be equal, But in the long term, whatever luck you have will eventually be overcome by the parameters of the game. So this phenomenon, if you're interested, this is basically the law of large numbers. So the idea that the more simulations you run, or the more instances process happens, the more the average value of all the instances will approximate the so-called true value. So this is easily demonstrated by MCS to simulate spins, right? So I will come back later to how all this has to do with language. So just be patient. I'm introducing the fundamentals of the method. Right, so basically, it's a simple demo in Python. So MCS can easily be implemented in the programming language like R, Python, or even Excel, actually. So for each spin, imagine the house will win or lose either $1. So so basically, if you win, the house pays you $1, and if you lose, you pay the house $1. So it's reciprocal, right? So basically, this is a very simple program. What it does is it picks a random number n times to simulate n spins. So over here, let's say we play the game 100 times, simulate 100 spins. So for each spin, we simply ask the computer to pick a random number, right, with equal chance of each. So it's a uniform distribution, random number from 1 to 100, right? So if the spin is less than or equal to 49, the house loses $1, right? If it's 50 to 100, then the house wins $1, right? So then we do this 100 spins, and then we repeat it 100 times to simulate 100 sets, right? So this is basically Monte Carlo simulation. So all you do is you begin by inputting the probability distribution, and then you just randomly generate all kinds of different scenarios to see what might happen in real life after all this simulation. So let's have a look at a distribution of the house winnings after different values for n and k, after a certain number of spins, a certain number of sets. So these are histograms. So let's say if we play 100 sets of 100 spins. So basically what happens is we spin the wheel 100 times, and then we calculate for each set how much the house has won. Remember, if the house wins one spin, it wins $1. If it loses one spin, it loses $1, right? So if you repeat this 100 times, this is the result. So what you can see here is that the expected winnings of the house is near zero, but actually already a little bit more than zero. So what this histograms means is that, for instance, the house winning is here 20. So, and number of sets is here. So for approximately 8 out of 100 sets, right, the house actually won $20, right? And in some sets, the house actually loses money, which means you actually win some money. But as you can see, if we repeat this for 100 spins and 100 sets, the odds are about equal. So let me just quickly demonstrate this in Python. So I hope you can see. So basically, it's just here, right? So this is the number of spins, and this is the number of sets. So 100, 100. So what happens is just, you get the histogram here. And every time you run it, it will be slightly different because it is random. Every time the result is a bit different, right? I can also change the game parameters, change the stakes a little bit, but we don't have time to delve into that too much today, right? Where are my slides? Okay. So if we repeat now with 1,000 spins instead of 100 spins. So why do I repeat 1,000 spins? Because I want to show you that the more you spin, the more the house actually is beginning to win more and more. So remember, you start off with almost equal odds, but if you keep spinning and spinning, right, the law of large numbers tells us that, okay, it begins to converge towards the actual expected value. The more you spin, now the house on average can expect to win about $30, as you can see. And it's very unlikely to lose to you this much. Okay. So if we keep going more and more, notice, so now if we play with 10,000 spins, you see it's basically a no contest. So the house is expected to win on average 300 bucks. So, almost 25 sets, the house wins $300. So basically the moral of the story here is that the more you spin, the more they win. So basically the idea for us is that, notice that when I keep repeating the number of simulations based on the initial probability distribution of 41% to 51% and 49%, the more spins I do, the more accurate of a picture I get about the true expected value. So this is how the casinos actually survive. Basically, they bank on you thinking that you are lucky in the short run, but if you keep betting, then this is what's going to happen to the house eventually. Okay? And finally, let me show you what happens if now we increase the number of sets instead. So this is 100 sets. So what happens is I simulated 10,000 spins 100 times to cover 100 different possible scenarios. If I repeat it, let's say 1,000 times, what do you observe? You observe that by simulating more and more sets, what happens is we are covering more and more probabilistic ground, and we get a more precise distribution. So what this means is that by simulating more sets, you are saying, okay, let's see what happens in another scenario, in another scenario, in another. Each of these scenarios is slightly different. But the more you do, the more probabilistic ground you cover, and the more likely you are to actually cover the various different scenarios that can occur. So basically, essentially, the more sets you have, the lower the margin of error is expected to be, inversely proportional to the square root of k. Right, so that gives you a brief point, I hope, about the nature of Monte Carlo simulations. So just to consolidate it a little bit further, let me just play around with. So let me show you what happens if instead of, so let's say if we just do 10 sets of 10 spins each. Okay, so this is not a very good simulation because you are using so few data. See, what happens is you get this kind of picture. This is not useful at all because this one basically is saying, okay, it's very sporadic, you see. Like you cannot infer anything based on this histogram by simply playing the game 10 times, spinning the game 10 times and playing it 10 sets. You don't get a good picture. You can't derive any useful statistical inferences from here, right? So the point is the more simulation, the more sets and the more spins, the more precise your scenario analysis will be, as I will show you.
Sorry, Dennis.
Can I interrupt? Yeah, sorry.
Yeah.
We can't see your screen right now. So the screen you just showed us, we're not able to see it. We're only seeing the top where it says Adobe Acrobat Reader DC. We're not really seeing the whole slide.
Can you see now?
No.
I think you're running a program on your computer, and you should use the share screen function to share this screen.
Okay,
so that we can see it. We can see the screen now.
Okay.
Everybody. So, but you just said people couldn't see the screen.
Okay, let me just repeat.
Okay, thanks.
Okay. So basically, what I was saying is, if instead of a large number like 1,000 spins and 1,000 sets, let's say now if we got the code here, I change it to just 10 and 10. So basically, what happens is I just want to play the game 10 times. So draw 10 random numbers and repeat it just 10 times. So you see, if I do this, let me run this code. I get this kind of very sparse kind of histogram, which is not useful at all. So what this tells us basically is that, as you can see, it's not precise at all. I cannot infer anything statistically from what is likely to happen. But if I increase the number to a reasonably large number, then the more you see, it starts to build up towards a normal distribution, which then we can use the statistical properties of a normal distribution to estimate what is happening. How likely are certain events to happen? Okay, so can you see the talk now? I'm back at the talk.
Yes, I can see the other PDF.
Okay, yeah. Okay, good. Right, so we are here. Sorry for that glitch. I'm not that familiar with Zoom actually. Okay, so what was the point of all that? You might be wondering at this point. So what I'm trying to do is to introduce the concept, but also try to show you, some of you might can already imagine how this can be applied to discourse analysis, perhaps. So what I did was, by generating many samples, right? So using the computer, I just generate numerous random samples, but not arbitrarily, but based on a known probability distribution. So this is known to us. These are the parameters of the game at the beginning. So we are trying to recreate what would have happened in real life anyway, without actually playing the game in real life, simply using a random number generator in Python to imagine, to simulate numerous times based on this known probability distribution, we get a picture of what is likely to happen in real life anyway. Okay, with large n, a large number of spins, because of the central limit theorem, a bell curve will emerge, a normal distribution. So once normal distribution emerges, we can use its properties to infer things. For instance, 95% of samples are within 2 standard deviations, and so on and so forth. with large K, large number of sets, right? So there's a difference here. This is the number of spins. This is the number of sets of spins, okay? So with large K, the more and more simulations I run, then the mean of all these simulations will get closer and closer to the so-called abstract construct known as the true mean, okay? The true mean, if we were able to do this forever, what is the true average value that the casino will win, right? So this is again the law of large numbers. So with these two things in hand, we can do a lot of things because we can conduct all kinds of scenario analyses. So for instance, like I said, we know that 95% of all scenarios will be plus minus 2 standard deviations from the mean of the simulations. So basically we can predict, for instance, 95 out of 100 times, the casino will not win or lose more than 2 standard deviations of the mean value. So this is basic normal distribution. And also we can infer that the true mean will be plus minus 2 standard errors of the mean from the mean of simulation. So this is basically the basic statistical information about a normal distribution. It's okay if you don't quite know what I mean, because it's the concept that is more important. And the concept is basically, I'm arguing that this exact same logic can be applied to linguistic data if you quantify it appropriately. So therefore, even with some gaps in your data, if you can run MCS, you can actually have a good scenario analysis based on the probability distribution. So that's my main argument. So now let's dive into the linguistic stuff itself. So like I said, now we are in a case study of psychotherapy, right? So psychotherapy is linguistically constituted, which means that people actually deliver and receive the cure, or so-called a treatment, via the medium of language itself. So it is a mental health activity, and it is divided into weekly. Most of the time is weekly, but of course it can vary. Sessions. So each session is basically a chunk of language, as you can imagine. So this is real data. So just to show you a sense of what psychotherapy talk is like. T stands for therapist, C stands for client. So as you can see, if you briefly read through this yourself, you notice that it's quite typical whereby the therapist is in kind of like questioning mode. Anything you're building right now that you're questioning, and the client basically responds in kind. And you can see from here that there is kind of uncertainty. The client is not quite sure what he or she is doing because he or she keeps questioning if there's anything there to build on. And then the therapist tries to clear the air, tries to elaborate what's going on, tries to interpret. And then again, the C here continues to use a very tentative language, as you can see. It's a whole bunch of wishes and ifs and maybes and possibilities, so it's not substantial at all. So this clearly, as you can see, the language used already is beginning to reflect certain variables, certain therapeutic progress and outcomes, right? So in other words, we can actually look at the quality of language to gauge or to estimate or to evaluate how well the therapy is going at a particular point in time. And also recently, I've argued that in order to analyze psychotherapy language, the most sensible unit of analysis is the session, right? For statistical reasons mostly, the session is actually the most sensible unit of analysis, and I won't elaborate why today. Right, so when we apply MCS, this is the analogy, right? Each session, think of it as a spin of the roulette, as I introduced just now. So what we are doing is we are trying to simulate the various different scores here based on a certain probability distribution at the beginning. So for the roulette, if you remember in our example, the probability distribution is a binomial distribution. It's just 51 versus 49%. Of course, for language, it's not so simple. It's not binomial, it's some other kind of distribution, but the concept is the same. What we do is we use the existing sessions we have, we simulate various other session scores, and then we do the scenario analysis as I showed you just now. Okay, so to quantify psychotherapy language, there are of course many ways to do so. So what I did was I used this program called LIWC, Linguistic Inquiry and Word Count, by Penny Baker et al., which is a very popular program in social psychology. So what it actually does is basically, it's essentially a word level sentiment analysis approach, program using a bag of words approach. So in other words, there is an existing large lexicon in the program, and what it does, it looks at every word in your database and it categorizes each word based on certain theoretical categories. And sometimes it's not just categorizing, but it's also based on algorithms where it assigns a score based on certain combinations of word use. Again, I won't go into the algorithm of this program today, but you can read the reference. Okay, so for our purposes, what we need to know is that what it does is if you feed the transcript to this program, it gives you an automated computation of several kinds of variables. So summary variables and linguistic variables. For instance, you can count the percentage of pronouns in the transcript, right? So today I just want to talk about summary variables, which are these four. So these summary variables are essentially basically summaries of how the language is in terms of 4 dimensions, how analytical the language is, how much power relations are reflected, how authentic the language is, and how emotional the language is. As you can imagine, all these variables are highly relevant to psychotherapeutic processes. So the interpretation is basically each of these variables is scored from 0 to 100. So each session will receive a score from 0 to 100 along these variables. So very briefly, right? So along the high scores, you can see the higher it is, for instance, the more formal, the more logical, the more hierarchical the language is deemed to be based on the word used, and so on and so forth, right? If you want the slides, I can send it to you later, but I don't have time to detail the table. Today, we just want to look at analytics using MCS on just one variable. So just a univariate simulation on analytic thinking, and the interpretation is here. So the higher it is, the more formal, the lower it is, the more informal. The kind of word use is informal, right? So I will show you examples, and if it's in the middle, it's balanced. So some of you already can see what I'm trying to drive at. So what I'm trying to do is basically to calculate analytic thinking scores for the sessions that I have, and to try to use Monte Carlo simulation to predict what would be the other scores if I were to have the data. In the absence of the data, using MCS to generate likely scores, right, for an analysis purposes. So to illustrate these variables, so let me just give you an example from everybody's favorite man nowadays, Donald Trump, right? So this is him proudly announcing to the world after he killed the ISIS leader on the 26th of October. And this speech was given in the following day, whereby he basically was telling everyone that he successfully assassinated the ISIS leader. So I'm not going to read through everything. Essentially, it's his usual style. You know, he talks a lot about how his military succeeded, and he was basically kind of like, this part struck me particularly. He died after running into a dead-end tunnel, whimpering and crying and screaming all the way. So this is just a short extract of what he did. So what I did was I subjected his whole speech to LIWC analysis. Okay, so this is basically the result. So you can see here, summarized it for you. It is a very high analytic score. Out of 100, 73.4 is very, very high, right? Above a lot of baselines. And clout as well, 86.61. So he's displaying a lot of power in his language, and he's displaying high analyticity. So if you read the transcript, you can see there's a lot of stepwise recounting. We first did this, we then did that, next we did that. So this accounts for the high analytic score. And he speaks, as usual, with a very authoritative tone. And this accounts for the high clout scores. Okay? Very low authentic, only 5 upon 100. And tone 1 upon 100. So very low. So what this means is that he uses a lot of guarded and distant language. So he doesn't open up his personal, he doesn't use very personal words. It's a very authoritative, guarded language, which with a lot of emotionally negative words. So if you're interested, this program is available as a sample. You can try yourself. Just Google LIWC. Right. Okay. So by applying LIWC to I can't show you too much psychotherapy data because in principle it's confidential. So, but what I did was, again, you see, I basically analyzed each session. Remember, the session is the most sensible unit of analysis. So I examined each of these variables, and each session has a score here. So what I did was I derived the probability distribution of each of these variables. Today, I just want to talk about analytic thinking. Okay. So again, the logic is, if there are incomplete sessions here, I shall simulate the missing sessions and scores using the probability distribution of the scores that I actually have. So this is analogous again to the roulette, right? We know in the roulette, the probability distribution is clearly defined, 51% to 49%. But in this case, we need to figure out what is the probability distribution of analytic thinking across the sessions that I have. And this is quite simple to do. Okay, so the steps of the MCS methodology is therefore like this. So again, the first step is what I just showed you, right? Compute the LIWC scores for each session using the program. And then basically, in this case, I have 43 sessions. I split it into 2 data sets. This is a very common practice in machine learning. So what you do is you have a training data set. It is this, so you use 40 sessions to train the MCS model, and you reserve 3 sessions as a test data set. So what happens is later on, you want to use the test data set, which is the real data, to see whether it can be accurately predicted with your training data set. So this is called cross-validation. Okay, and then you determine the best fitting probability distribution for each variable. So remember, in the roulette example, the probability distribution is binomial, right? In our case, as I will show you later, it is a normal distribution. Sometimes you will get a log normal, T, Poisson, whatever, right? So each case is different. And then what happens is you do the actual Monte Carlo simulation. What you do is you are trying to draw many samples, right? And to randomize this, what happens actually is that, for instance, if I want to simulate 40 sessions, I'm actually picking 40 random numbers from the interval 0 to 1, right? And then each of these numbers, I'm actually mapping it onto the probability distribution here. So in this case, if the distribution is normally distributed like this, what really happens is, to keep the technical details simple, I'm just picking 40 random points along this curve to simulate the random linguistic phenomenon. So if I have 40 sessions, each of these sessions has a certain chance to be picked along this whole normal distribution, right? And then we can use further techniques to improve the process, such as variance reduction, which I won't go through today. And then this is one particular set. So I draw 40 sessions for one set, and I loop this whole process k times. Remember, k is the number of sets. And then finally, I plot the histogram. So it's exactly the same as my casino roulette example. All right. So this is basically, sorry. So this is basically step 3. From my sample data, remember my sample data, I have 40 sessions, right? From my sample data, this is the score. This is the analytic thinking score. So remember, the analytic thinking score is from 0 to 100. So basically, this is truncated to show the bulk of where the data is, right? So using the Kolmogorov-Smirnov test, basically it's a distribution fitting statistic. We determine that it best fits a normal distribution, this sample data. And with a normal distribution, some of you will know there are 2 parameters, the mean and the standard deviation, which are these 2 accordingly. So this information here is exactly analogous to the roulette information. So remember, in the roulette, it is a binomial distribution with 51% to 49%. For analytic thinking in the data set, it is a normal distribution with the mean of 19.7 and a standard deviation of 7.643. So with this information, I can do my Monte Carlo simulations. So I loop this 10,000 times, as you see here. I loop this 10,000 times, and this is the scenario I get. Okay, so what happens is, each of these 10,000 times, in the discourse analytic perspective, we can construe this as a discourse scenario, right? So each one has a slightly different probability of occurring. But the point is, each of these discourse scenarios, actually, they all converge to tell us, overall, this is the likely picture. The resulting model is the likely range analytic scores in the absence of actual data. So what this offers to the therapist is that even though, for instance, the client doesn't show up for many sessions, or the client totally disappears and comes back again much later, which is quite common in real life, you can run Monte Carlo simulations to get a good estimate of how likely the analytic scores are going to be. Even though you don't actually have the actual data, you can estimate it using Monte Carlo simulations like this. Okay, and then the next important step is cross-validation. So remember, I reserved 3 sessions as a test data set. So what happens here basically is very simple. So the test data set in principle should be about 20% the size of the training data set. The basic logic is, I have the model scores, or I have the model mean. So all these, I have this model mean, the model standard deviation. And basically the idea is, if the test data set does not differ significantly from the model scores or from the simulated scores. So for a normal distribution, we know that basically this means if the test data set is within 2 standard deviations from the simulated score, we can claim that the model is accurate for working purposes. Okay, so what I do is I analyze for each variable. So as you can see here, it is not always accurate. The Monte Carlo approach is accurate for most variables, okay, across 2 different diets, okay, but except for, or rather with the exception of these 2. Okay, so for these 2, you can see that the test data set mean is actually significantly different from the model data set mean, which means that the data is not accurate enough to capture the real life scores. But for most other cases, it is okay. But of course, if we want to be perfectionists, we must aim towards making sure that all variables are okay, but that's not as easy as imagined. Okay, so another verification approach I would like to share is, this is just another way to looking at it. So if the real mean value is known, so if you have a complete data set, and you just want to test this approach. So in a complete data set, let's say this is actually the real mean of all the sessions, right? We can see that from this approach, you can see the number of simulations, the number of sets you need to converge towards the real mean. You can see here, if I run very few simulations, it fluctuates a lot. And this is expected because if you just run a few simulations, you're only capturing very few discourse scenarios. But if you run up to 1,000 simulations, you can see it actually converges towards the real mean, which means that in this case, 1,000 simulations is sufficient to get a very good estimation of the real mean. Okay, so this is good timing. I'm about to finish. So what can we do with the model, right? So for linguists, for researchers, language researchers like all of us, and also for practitioners. So for researchers, the most obvious application is to simulate scores, to plug data gaps. So in my case study, the data gaps refer to missing sessions or even prospective sessions that have not happened yet. Okay, it can complement other forecasting tools. So for instance, if you are familiar with ARIMA time series modeling, you can basically use Monte Carlo to complement ARIMA models, which are more sensitive to more localized fluctuations from sessions to sessions. And I wrote quite a bit about that. Okay, and for researchers, again, a very important use is this kind of approach provides very interesting entry points for further qualitative analysis, which I don't have the time to explore further, but I'm very happy to discuss ideas with you. So for practitioners, in this case, the practitioner will be a therapist. Of course, if you are dealing with call centers or classroom discourse, you have a different set of practitioners, but the general principles I think are similar. So for therapists, prognosis means trying to predict the symptoms, or rather trying to predict the cause of the disease. So in the medical context, you're trying to say, how likely is the patient to recover? In the mental health context, it's the same thing. How likely is the patient to behave in future sessions? Based on the model, the therapist can have a reference point. For instance, fluctuations. Fluctuations are very common in therapy because it's very hard to sometimes to be sure of how the client is likely to talk, especially for certain people with conditions like, for instance, bipolar disorder. It's very difficult to get a good grasp of how likely the person is going to behave linguistically. But with the aid of this model, we know that the fluctuations are unlikely, not impossible, but unlikely to move beyond confidence boundaries of the model. So to be more technical, in our case specifically, we know that 95% of the time, the client's analytic thinking is not likely to go beyond 19.769 plus minus 2 times the standard error of the mean of the model. So this may be useful in certain cases. And also training. Training is a very important aspect of psychotherapy, of all professional discourse. So we can use the simulation models as a kind of benchmark or reference point. So imagine if we use professional practitioners, the language of professional practitioners as to build our simulation model. And then we monitor a junior or novice or trainee therapists through their role-playing exercises, and then we measure their performance. We can use that to compare how the trainees' linguistic behavior differs from the simulation models derived from expert behavior as a kind of performance measure. And this is particularly useful from a paradigm-specific point of view. So we know in psychotherapy, there are more than 400 different types of therapy. So from a comparative perspective, you can see, to what extent the way you're talking resembles the way you're supposed to talk from the assumptions of your specific therapy paradigm. So I'm not an expert at all in any other professional context. So, but I would claim that the above points are transferable in some way across different professional and discourse contexts. Okay, finally, limitations and drawbacks. The most obvious limitation is computational expense. So today I'm very conservative. I only show you 10,000 spins. But if you want to be very accurate, if you go up to, let's say, 1 million, you can expect to wait for a long, long time because the computational expense, there's exponential increase in the runtime as the N and K increase. So this is one thing that is a drawback. Okay, and then the next one is a bit more conceptual. There is still a conceptual gap between statistical probability and so-called linguistic probability. So today I showed you statistically the notion of so-called discourse scenarios and discourse conditions under which the scores deviate. But to map this onto discourse conditions is still a difficult thing. So how to articulate the so-called discourse scenarios or conditions under which scores deviate. So this is a big project that is not easily doable in the near future, but eventually we'll get there. And then to evaluate the relative advantage of MCS over other solutions. Remember at the beginning of the talk, I showed you some possible solutions, one of them being role play. So the relative advantage of MCS over role play needs to be proven. So this can be done, for instance, by, again, using the cross-validation method. But I so far have not done this because I don't have any role play data. Okay, and the last thing is that MCS models for language, at least in my data, in my psychotherapy data, are far, far less accurate than models for financial data. So I have some background in this area. I studied a bit of econometrics, and we can see quite clearly that linguistic data is far less modelable, so to speak, than financial data. And this obviously is not surprising because language is messy inherently, especially discourse. But I still believe that the method is worth further explorations in different discourse contexts. And if you would like to discuss it with me, you're more than welcome. So that's the end. These are the references. If you want to read any of these, just let me know. And